Okay, thanks. Okay, so let us continue from what we were discussing yesterday. So we were discussing semaphores. So just a 2-minute recap maybe. Though, so semaphores are essentially a mechanism for mutual exclusion. That means to ensure mutual exclusion. So semaphore is essentially a lock. So you can decide how many processors can or threads can simultaneously get a lock. That means suppose you just want one process to get the lock, then you initialize semaphore to 1. So essentially semaphore you can think internally is an integer value, though a special integer. So the speciality will come out. So the speciality will come out in the fact that basically you can do two operations, increment and decrement, but these are atomic, right? So technically these are called wait and signal. So wait is you are trying to reduce the value of the semaphore, but this whole function is atomic. Similarly, wake up or signal, signal, that is you are trying to increase the amount of the semaphore by 1, but again it should be atomic. And also apart from increasing and decreasing, there are other things like if you want say a simple semaphore, which we call a binary semaphore, then you can initialize it to 1. Then when one process gets the semaphore, that can enter the critical section. Other processes, when they wish to get the semaphore, they will wait. That means they will be added to a waiting queue of processes which are waiting for this semaphore. Okay, so that is how we avoid busy waiting. So we earlier discussed a implementation of semaphores where there was busy waiting. So we had a while loop. So like while the semaphore value is less than 0, less than equal to 0, wait. That means if we just had a semicolon, so basically it's a busy waiting kind of thing. But then we discussed that busy waiting is inefficient. Therefore, we would like to make the processes waiting for this semaphore actually go into the waiting state. There is no point in giving those processor cycles. Okay, so this is what we have discussed. Also, we understood that semaphores have some problems also. So it depends on, so they are not inherent to, the problems are not inherent to the semaphores, but basically how you use them. So if you are not careful, then you can have situations like this, where say P0 is waiting for P1 and P1 is waiting for P0. So P0 is waiting for a semaphore which has been obtained by P1. Conversely, P1 is waiting for a semaphore which has been obtained by P0. So they will both continue waiting for each other. This is a deadlock situation. So as I said, if you are not correct using semaphores correctly, then there can be problems. Like first you write signal and then wait. It should not be the case. Or you forget to signal a particular semaphore. So the other processes will get stuck, right? And therefore, if you are not careful about how you use semaphores, then deadlock and starvation are possible. But yes, semaphores are very useful entities. Therefore, if you use them carefully, you can actually solve many problems like what we discussed yesterday. Like not only mutual exclusion, but also synchronization between two processes. Like you want the process 1 to do something before process 2 can proceed. So these kind of things you can do with semaphores. Now let us look at briefly some actual like library implementations of semaphores. So again, we have discussed this word POSIX earlier. POSIX is a family of standards. So POSIX also defines some standards for semaphores. So like you had POSIX pthread library. So the pthread library followed the POSIX standardization on threads. Similarly, there are POSIX semaphores which follow the POSIX guidelines on semaphores. So for using them, you have to hash include semaphore.h and you have to compile that code by using -lp thread -lrt. Okay. Okay. I'm a bit okay. Okay. I'm not very sure. Like if you are not using threads, you might not have to compile with -lp thread because you can use semaphores with processes also. Okay, this part I'm not very sure. It might be a bit of a, like, this is correct. Like if you do it, it will definitely work. But if you are not using threads, you should not need a minus LP thread. Anyway, maybe when you are writing the program, you can check once. Okay, so there is this data type sem underscore t, and you declare a semaphore like this. And then you initialize the semaphore using sem init. Okay. So again, these are the parameters. So basically the semaphore to be initialized. This is an interesting thing, be shared. Right? So whether or not this semaphore will be shared between processes or between threads. So essentially understand that usually no one declares a semaphore just for use with a single process. Because what is the process going to synchronize with? Or what is the mutual exclusion question if there is only one process? Right? So semaphores are kind of intuitively used when there are multiple processes or multiple threads cooperating with each other. Therefore, this pshared variable enables you to indicate whether the semaphore can be accessed by other processes or whether it can be accessed only by the threads belonging to this process. Right? And you have a value. So we discussed this thing that depending on your application, you can think of a binary semaphore where the value is 1 or 0. Or if you want a counting semaphore, then you might initialize the semaphore to a higher value. Like you can initialize the semaphore with value 5. So this is the sem init call. Then there are system calls for this wait, signal, and destroy. So sem underscore wait is you wait on a semaphore. And signal says sem underscore post. So sem underscore post is used for signaling a semaphore. And then you can destroy a semaphore. So again, I'm not going to the details of these calls here. Look them up, like most possibly in the laboratory assignment when some lab assignment will be given, then you would need to use this kind of system calls. Okay. Fine. So that was about the kind of implementation or coding part, which possibly will be more explored in the lab. Now, here we will just discuss some classical problems of synchronization. So classical problem means essentially these are very well-known problems. And if you are trying to design a new synchronization mechanism, then you will have to at least show that these problems are solved. Okay. So I'm sure you have heard of benchmarks, right? So you can think of these are benchmarks. So if a new algorithm is being proposed or a new, say, nowadays new processors are being proposed every day, right? So say even when a smartphone comes out, how powerful is the processor in the smartphone? For that, there are some benchmark tasks which people do and report their results. That how much time did this task take? Right. So that is kind of benchmarking. So these three problems which we are going to discuss. These are kind of benchmarks in synchronization. Here we are of course not worried about the time taken to solve, but we are saying that if you are proposing a new, synchronization mechanism, then that mechanism should at least be able to, should at least be correctly applicable to these problems. Okay, that is why these are important, like these are historically important problems which people have tried to solve. So let's understand. The first one actually we have seen earlier, but let's see still. So a bounded buffer producer consumer problem we have seen. So there is a buffer of a finite size. A producer or multiple producers want to write to it, and consumers want to read from it, right? Okay, I think here we are for simplicity considering one producer and one consumer. Though in the third problem, we will generalize the situation further. So bear with me, okay. So yeah, so here there is only one producer and one consumer, and there's a bounded buffer. And because the buffer is bounded, the producer and consumer need to keep track of how many elements have been filled and so on. So if the buffer is full already, the producer should not try to write more. Or if the buffer is empty, then the consumer should not try to read from it. So how can we solve them, say, using semaphores? So let's say there is n n is the number of buffers. Like, so we discussed about a circular queue, if you remember. So there are n elements. So there are n buffers. So we will use 3 semaphores. By the way, let me just clarify. I'm not claiming that this is the only way of solving the problem. You can think of other ways. Right? But this is one way which is kind of easy to understand. Therefore, the book gives this. That is what we are discussing. But sure, there can be other ways of solving the same problems. Okay, so we have 3 semaphores here. Mutex, full, and empty. Mutex is initialized to 1, full to 0, and empty is initialized to n, where n is the number of buffers. Okay, so the semaphores empty and full, the purpose is to count the number of empty and full buffers, and mutex is like providing mutual exclusion, because again, we don't want the producer and the consumer to simultaneously access the buffer. Okay, so yeah, we do not want the producer and consumer to access the buffer simultaneously. Again, let me repeat. Take the word simultaneously with a pinch of salt. Actually, this is not happening simultaneously. Okay, we know that in a uniprocessor system, at one point of time, one process is happening, one process is running. Therefore, when I say simultaneously, like understand that abstraction, that we are not exactly talking about simultaneously 2 processes running, but if one process, let's say the producer has started doing something with the buffer, then even if it gets swapped out of the CPU, even if it gets deallocated from the CPU, we do not want the consumer to update the buffer right now, because maybe the producer has not completed updating the buffer yet. So that kind of a, so I'll continue saying simultaneously, but have that abstraction in mind. Okay, so this is the structure of a producer process. It first waits on empty, okay, because it is wanting to know, it wants, okay, so see this process, this producer process is first waiting on empty. So what do you think? So how do you think this will proceed? As in, when will this wait empty? When will this be successful? As in, when will the producer be able to get this semaphore empty? Get this means we'll be able to actually reduce its value and proceed. When do you think the producer will be able to get this semaphore empty? Exactly. Shashutosh has given the right answer. So if you see, we said empty has been initialized to n, right? So the first n items, the producer will be able to directly wait. So you see this empty semaphore, it has a value of n. So the producer will be, like, even say the consumer is not consuming anything, even then the producer will be able to get the semaphore empty n times at least, because there are n empty buffers. But then it won't be able to get the empty semaphore anymore because the buffer is full. Henceforth, the producer will only be able to get the semaphore empty when the consumer signals it. So you have not seen the consumer code yet, but intuitively understand that empty should be signaled by the consumer. So the signal is basically increasing the value of a semaphore. So when consumer consumes an item, it signals empty. That means it increases the value of empty. Then the producer is able to add one more item. Okay. And conversely, if you see this process, this producer at the end signals full. That means it increases the value of full by 1, so that the consumer knows that one more item is again available. Okay. So if I just go on to the previous slide once, if you see the consumer, this is exactly the mirror image kind of thing. And this is first waiting on full, which is signaled by the producer. Okay. Let me just So this slide, the consumer waiting on full. And if I go back to my previous slide, the producer process, this is signaling full. And conversely, the producer you see is waiting on empty. If I go to the consumer process, this is signaling empty. Okay. So this is the synchronization we want. Producer is telling the consumer that one more item has been added by increasing full, and consumer is telling the producer that one more item has been removed by signaling empty. Right. And there is this mutex semaphore. Understand, this is because we do not want the producer and the consumer to simultaneously update the buffer. Therefore, both of these waits on mutex. See, both the consumer waits on mutex, and after removing the item, it signals mutex. Similarly, the process producer waits on mutex, and after updating the buffer, it signals mutex. Okay. So the producer and the consumer. Is this fine or any questions? Okay, let's proceed. So this is the bounded buffer problem or producer consumer problem. It's pretty simple. Let's go on to the next classical problem of synchronization, which is called the dining philosophers problem. Okay, so why philosophers? Well, historical reasons, but I guess just see the description, then you might get an idea. So philosophers spend their lives alternating thinking and eating. Not exactly, but yeah, in this problem, that's a simplified scenario. So philosophers, yeah, don't like to talk much, so they don't interact with. So on a table, there are 5 philosophers sitting. Let's say 5 is just a number. We'll explain the problem using 5. There can be more. So 5 philosophers are sitting at a table for eating. However, they don't talk to each other. So just when they are thinking, and when they are hungry, they try to eat. Now for that, this whole problem originated from Japan, and you know chopsticks are like they give rice and they use chopsticks to eat rice. So essentially, when a philosopher wants to eat, they have to try to pick up 2 chopsticks, one at a time, to eat from the bowl. So actually, yes, so there are these 5 people sitting and they have 5 bowls in front of them, bowls of rice, and there are 5 chopsticks only available. Okay, of course, you might ask, why not give them 10 chopsticks to each? Then the whole problem would be solved. But yeah, I mean, then there is no problem actually. So in this problem, there are 5 chopsticks and 5 philosophers. Right? So suppose you are on a very tight budget, so you can only afford 5 chopsticks. So the issue is that the philosophers, so one philosopher when he wants to eat has to pick up 2 chopsticks. Right? So that is the condition. Need both chopsticks to eat. And then release both when done. Okay. So let's say we will consider the example of 5 philosophers and 5 single chopsticks as shown in this picture. And therefore, there will be 5 semaphores. Let's say 1 for each chopstick. Okay, and see, a chopstick can only be taken once. Therefore, chopstick. So we have this 5 semaphores all initialized to 1. Again, let me clarify. This is not the only solution to the problem. Some of you might say, hey, can't we have just 1 semaphore with the value 5? Maybe you can. Feel free to think on those lines. But we are just describing a simple solution, which is easy to understand. There can be definitely other solutions. Okay. I hope the problem is clear. So 5 philosophers and 5 chopsticks. The issue is one philosopher when wants to eat has to pick both, right? So if you see this philosopher, so this one, by the way, one quick point. Is my the mouse pointer visible? The one which is moving? Okay, great. Thanks. So if this philosopher grabs both these two chopsticks and starts eating, then these two some philosophers are blocked. That means they cannot eat. Okay, that is the kind of the mutual exclusion problem. If this philosopher sitting here at the bottom has already grabbed these two chopsticks and eats and has started eating, then these two philosophers are blocked. By the way, we are assuming here that philosophers are very disciplined people. So this philosopher will not try to jump and get this chopstick. Right? They will only eat when both the chopsticks near him or her are available. That is why when this philosopher has grabbed these two chopsticks and is eating, these two philosophers cannot eat because they won't get two chopsticks. Okay, this is the problem. So now let us see the solution. Of course, I hope you understand this problem is not at all practically used for philosophers and chopsticks. Other practical problems are mapped to this problem, and then like this kind of synchronization is applied. Okay, so let's see the problem. Let's see the solution now. So this is the structure of the philosopher I. Okay, waits on two chopsticks. Which two specifically? So this is the philosopher I. So this is the pseudocode for philosopher I. Okay, where I is say 0, 1, 2, 3, 4. So it waits on chopstick I, waits on chopstick I plus 1 modulus 5. Right? That means a philosopher 0 waits on chopstick 0 and 1. Well, philosopher 5 waits on philosopher 4 waits on chopsticks 4 and 0. Okay? 4 plus 1 mod 5 is 0. Then eats and then signals the two chopsticks again. Simple. But then there is a problem with this algorithm. Can you identify what? If you have any questions, ask. Otherwise, like this is a question from my side that there can be a problem with this algorithm. So what is it? Okay, yes, very good. So Neha and Deep, and Ashutosh also. Yes, they have given, we have all given the correct answer. So imagine that okay, let me just go back to that picture once. Yes. Imagine that everyone grabs the chopstick to the left, to his or her left side. Okay, every philosopher grabs the chopstick to his or her left side. Then all philosophers pick up one chopstick, and no one is able to eat. Because you cannot eat with one chopstick, you need two. Right, so assume that this can happen, like worst case scenario, but this can happen, that every philosopher process just executes this instruction, and then the processor is allocated to some other process. Likewise, every philosopher process executes that one instruction, and then the processor shifts to another process. So at one point, it happens that all the philosophers have got, say every philosopher I has got the ith chopstick. So no philosopher can get two chopsticks and no one can eat. Therefore, this will be a deadlock situation. Okay. I hope the problem is clear. So good answer, Nehadeep, Ashutosh. So what can you do? What can you do? Some simple, I mean, Some simple techniques maybe which can be used to solve or prevent such deadlock. You're not looking for anything very complex, like some heuristic approach or something. Okay, if anyone wants to just unmute and say, maybe Neha, Deep, Ashutosh, if anyone wants to unmute and say, so what can be done to prevent this?
Sir, if we increase the time quantum for the process, then the process will not be interrupted between the two weights. If both the weights,
Wait, see. Again, that is a risky solution. Because again, understand that who is this? Oh, Ashutosh.
so it's deep.
Deep, okay. That is a risky solution. I mean, again, we have been telling this from the start of from quite a few weeks earlier. It's risky to assume those things that my process won't be interrupted between these two calls. That depends on the scheduler. I mean, that kind of a solution is usually not advised, where you are assuming something that the scheduler will not interrupt your process between these two instructions. That is not a very practical solution. Okay. Okay. Yes. Yashika has some suggestion. Okay. And Ashutosh is telling. Yeah. So something like what Ashutosh and Yashika were telling. So Deep, if your solution could have been done, it would have been good, but that is not a very practical solution. Okay. So let's go to the next slide. So how can you handle deadlocks? Okay. One thing is keep one more chopstick than the number of philosophers. Sure. The other things are exactly what like Ashutosh said or Yashika said. You might make this rule that a philosopher should pick up the chopsticks only if both are available. So just because one is available, pick it up, don't do that. Okay. Or use an asymmetric solution. Like an odd numbered philosopher picks up first the left chopstick and then the right chopstick. And the even numbered philosopher picks up the right chopstick and the left chopstick. Okay. So again, we are trying to reduce the probability of such things happening, that every philosopher picks up one chopstick to the left. Okay. So these are some like heuristic approaches to prevent these deadlocks, potential deadlocks. Okay. So yeah, that is the running philosopher's problem. Again, it has several practical applications. You might look up the book or the net. But yeah, I mean, when explaining, we talk about dining philosophers, but actually many practical situations can be mapped to this problem. Essentially, whenever you talk about shared resources, then these kind of problems can happen. Okay. Let us move on to the last problem that we will discuss, the last classical problem, readers-writers problem. If you think this, you can think of this as a generalized version of the producer-consumer problem that we discussed. But it is a bit more complicated. So let's see. So a dataset is shared among a number of concurrent processes. And there are two types of processes, readers and writers. Readers only read, they do not perform any updates. Whereas a writer can both read and write to the data structure, to the dataset. The problem is multiple readers can be allowed to read at the same time, but a writer must have exclusive access to the shared data. I think this is intuitive. So the readers, like it's like a notice board. So many people can read together, no problem. But if a writer is writing, or again, remember, there are multiple writers. So if one writer is writing, no other writer should be allowed to write. Okay. Now, there are multiple versions of this reader-writer problem. Okay, there are several variations, and the variations are mainly based on who is given priority, producers or consumers. Sorry, readers or writers. Okay. The first variation of the reader-writer problem is this: no reader is kept waiting unless writer has already obtained permission to use shared dataset. Okay. So no reader is kept waiting unless writer has already obtained permission to use the shared dataset. So when writer has got permission, then of course readers need to wait. That is understandable. But I mean, unless the writer is writing, no reader should be kept waiting. So okay, and what's the second variation? Okay, and so the second variation is that once the writer is ready, it is immediately or as soon as possible allowed to write. So if you see in the first variation, readers have priority, whereas writers may starve. And in the second variation, the writer has priority. Okay. Now again, don't start thinking which is correct. There is nothing correct or wrong here. Completely depends on your application. If your application demands that writers have priority, then you go for the second variation. If your application demands that readers should have priority, then you go for the first variation. Right, so it completely depends on what your application needs. In this lecture, we discuss only the first version or first variation of the reader-writers problem. So in our case, readers have priority and writers may starve. Okay, so let's see. So readers and writers share the following. So now we are talking about one potential solution. Readers and writers share the following data. The data set, of course, which is to be updated or read. And then we have these three semaphores: RW mutex, and read count. So RW mutex is specifically used as mutual exclusion semaphore for writers. Right. So understand this, that actually readers do not need to mutually exclusively access the dataset because multiple readers can be allowed to simultaneously read. But writers need mutually exclusive access. Therefore, this RW mutex is used as the mutual exclusion semaphore for writers. Readers don't need any such mutex because readers, the critical point is the writers. Like when a writer needs mutually exclusive access, not the readers. So RW mutex is used as the mutual exclusion semaphore for writers. However, there is this integer read count. Okay, there is this integer read count used for a certain purpose, which will be clear. That is a shared variable. Okay, and whenever you have a shared variable which you want multiple processors to update, there can be a race condition there. Okay. So we need a semaphore to protect access to this read count variable. So semaphore mutex is used to ensure mutual exclusion when read count is updated. Okay. So for what is read count used, we will come to that. But this is an integer. This is not a semaphore. This is an integer. Okay. Which will be, as we will see, which will be updated by multiple processors. Now, whenever you have an integer or a data item updated by multiple processors, you need to protect access to it. Therefore, we need a semaphore which is mutex. Right? So RW mutex and mutex has two different purposes. RW mutex is actually used for mutual exclusion to the dataset, but mutex is used for mutual exclusion of this read count variable. Okay. Now, the process of readers and writers would come up, which is a bit complicated, but I want you to spend some time to understand that. Structure of a writer process is very simple. So basically, it waits on this RW mutex semaphore, then writes, then signals. Okay, waits on RW mutex, writes, and then signals. As simple as that. Note that the writer has nothing to do with read count variable or the mutex semaphore. Okay, the writer has nothing to do with the read count variable and the mutex semaphore. Mutex is used specifically for protecting access to read count. So since the writer does not need to access read count, it does not need to access mutex also. Okay, does not need to access mutex. Now the reader process, which is complicated, but take some time to understand what is going on. So this is the structure of a reader process. Okay. Take a couple of minutes to understand, then I'll ask you some questions. At this point, you do not please ask questions. Take a couple of minutes to go through this, then I'll ask you some questions, which will hopefully help to clear this. Clearly understand this. Okay. Hopefully you have seen this. Now, my first question, what do you think is read count being used for? Read count in value integer. What is that being used for? Maybe you can unmute and say someone, but then if yes, again, it's a mutual exclusion problem. So if multiple people start talking together, we won't be able to hear anything. But yeah, if anyone wants to unmute and say for this part, you can say. What do you think is read count used for? Okay, Ashutosh is saying how many readers want to read data. So Ashutosh, unmute yourself. Why is that important?
Sir, like basically, as far as I could understand, so when we have a writer and a reader will come in, so then the first reader will increment the read count by one, and then it will wait on RW mutex. But if another after this, if another reader comes, then it won't wait on RW mutex. It will simply wait on mutex. I also have a doubt there regarding like how it's functioning, but yeah, basically I get read count is doing that to ensure that the first one waits on RW and the others don't wait on RW mutex.
Sorry. Yes, you are logically correct. So actually you have also answered the question which is written on the slide. So yeah, so first of all, yes, read count is being used for uh, noting that how many readers are wanting to read. Okay. And the second question which we had is what is written in the slide, which Ashutosh has kind of answered. But suppose a writer is in the critical section and n readers are waiting. So if a writer is writing, then readers cannot read. So n readers are waiting. Which readers are queued up on which semaphore? There are two semaphores, right? Mutex and RW mutex. So which readers are queued up on which semaphore? So, okay, Ashutosh, or someone else, can you give once more the answer to this question? Which readers are queued up on which semaphore?
So the first reader will be queued on RW mutex and
Mhm.
others will be queued up on mutex, I guess.
Yes, exactly. So one reader is queued up on RW mutex, and the rest n-1 readers are queued on mutex. The rest n-1 readers first have to update that read count variable, and therefore they are queued on mutex. And the first reader, read after the writer started writing, that is queued on RW mutex. So you see, the RW mutex will be signaled by the writer. Therefore, the reader which is waiting on RW mutex will be able to get the read. So, so if you see, so remember we said, let me just go back to a couple of slides. Yeah. Remember we said we are discussing the first variation of the reader-writer problem. That means readers have priority, writers may starve. Readers have priority, writers may starve. Okay. So can you say how that is happening? Like what makes this true that the readers have priority and writers may starve? If anyone wants, you can unmute and say directly for this part.
Sir, RW mutex is signaled only after a read is completed, while writers will wait on RW mutex at the beginning of the write. So it is possible that the readers have that means the readers have higher priority.
Okay. Who is this? Who is this?
So Deep.
Okay, Deep. Okay, you are on the right track. Think a bit more. So you are okay. Repeat what you said.
So because the RW mutex is signaled only at the end of the reader process, so only after one
Wait.
is performed.
Think a bit here. You are on the right track, but think a bit. When is RW mutex signaled? Just when one reader has completed reading.
Yes, sir.
See the slide carefully. When is RW mutex signaled? Just after every reader has completed reading, or is there some other condition?
So it will be signaled when all the readers have completed.
Exactly. If read count equal to 0, then signal RW mutex. Okay. So everyone, think about this point. Why? Possibly RW mutex, we want it to be signaled when no reader is waiting. And that is how readers have priority. Like if readers are waiting, RW mutex won't be signaled. RW mutex will be signaled only if no reader is waiting. So essentially read count is kind of counting how many readers are waiting. How many readers want to read data. So if that is 0, only then the writer would be allowed to write by signaling RW mutex. And the writer is waiting on RW mutex. Think about it. This might take a bit of time to understand, but yeah, I hope this discussion will help everyone. So RW mutex is not just signaled just after every reader has read. There is a specific if condition there when RW mutex will be signaled. Okay. And that is how the priorities are decided. If readers have higher priority than the writer. Okay, right. So yeah, basically that is the discussion. So yeah, so this is a summary of all what we discussed. So we discussed about rest condition. We demonstrated it through a small problem. The rest condition typically happens because of two reasons. One is that when we write a high-level instruction, that actually gets broken down into multiple machine-level instructions lower down, and we cannot guarantee, or we cannot, we have no way of knowing when a process will be context switched. It might happen that one high-level statement got broken down into 4 lower-level instructions. Just after 2 of those lower-level instructions were completed, this processor got deallocated from the CPU. These things can happen, and these can lead to race conditions. So formally, we defined the critical section problem with its requirements, and then we discussed various solutions to the critical section problem. The very first was a complete software solution, Peterson's algorithm. Theoretically correct, but with the modern computer architectures, which allow out of order execution, etc., it's not always, it cannot be guaranteed to be correct always. Therefore, you basically need hardware support. So you need some instructions from the hardware which are guaranteed to be atomic. So that problem won't happen. That this instruction got broken down into 4 machine level instructions lower down, and just after 2 of those 4 instructions, a process got deallocated from the CPU. That won't happen. This is atomic. Either it will be done or not. You will come across the same concept in databases, if not already. Like there are also transactions need to be atomic. Right? So you have these acid properties and all in the database. So one key requirement is that a transaction needs to be atomic. So here also. And then we discussed mutex locks and semaphores. So basically mutex locks and semaphores are programming constructs, so easier for programs to use, but underlying they also use some kind of atomic instruction, right? Okay, now any questions? Okay, if not, let me just make that announcement so that maybe there will be questions after that, I'm sure. So next week is the exam week. So we won't have regular classes. So Wednesday and Thursday, we are not having classes. Friday will be the class test, the theory class test during this class hours. And yeah, we'll send out detailed instructions on what you need to do. But I have told you the basics. Syllabus would be up to this, up to what we discussed today. And it will be a proctored exam. That means you are expected to keep your video cameras on throughout the duration of the test. And then you will be assigned like online exam rooms, basically Google Meet links or something like that, where you will have to log in during the test and you have to keep your video cameras on so that we can see you. And then you write the answers using pen and paper, and then you scan those answer scripts and upload to Moodle. We will send you out detailed instructions. Any questions about the test, etc.? Yeah, and in the test, you can expect like short answer questions, numericals, based on what we discussed. Then maybe multiple choice questions, this kind of thing. So we won't give like describe Peterson's algorithm. I mean, those kind of questions won't be given where you have to memorize a lot and just write. Basically, the questions would be targeted to test your understanding of the concepts discussed in class. So it's not a question about memorization. Like, okay, some short definitions might be asked, but we would not ask like to describe a huge algorithm or those kind of things would be asked. So short answer questions and basically targeted to test your understanding of the concepts that have been covered. So any questions? Okay, if not, fine. Thanks everyone. So after today, we will directly meet on Friday for the test and we will send out instructions, detailed instructions and all. If you have any questions, feel free to ask on Teams or and mail us. Okay then, thanks everyone.